we are okay. So let me hit a control. No. Yeah, that's good. Question is, what do we do in the realistic case? Okay, realistically, you are not really summing series like like those funny series we looked at, 1 minus 1 plus 1 and so on, or 1 plus 2 plus 4. Okay, because in these cases, you know all of the terms in the series. Okay, you have a formula for the nth term. So if you're summing a series like this, sum of a sub n, you have a formula. Okay, you actually know a sub n is some well-known function of n. And that, if this is the case, I would classify such a problem as being an easy problem. Okay, I mean, if you can actually find all of the terms in a series, well, what's the challenge in that? That's no big deal. Okay, so the real life case is that you are doing perturbation theory. Okay, so you have a hard problem. You insert an epsilon. The answer is now a function of epsilon, and you have a perturbation series of that type. Okay, and of course, at the end of the calculation, you're going to set epsilon equal 1, or you're going to set epsilon equal to whatever its value is. Maybe it's 2, something like that. And your problem has now become, you started out with this hard problem here, and the problem has ended up that you have to sum this series, okay, and you really don't know all of the terms in the series. You only know 5, for example, or 10, or 3, something like that. If this were quantum field theory, you'd be lucky to know 5. Only in a few rare cases have people been able to get up to the 5, what is called the 5-loop calculation, or the 5th order calculation. So, so the problem is not just having an infinite number of terms in the series which diverges and finding a machine that turns that into an answer, but having a finite number of terms in the series, and your objective is to take each new term and invent a machine that takes you closer and closer and closer to the answer. And I gave you a quick example of how that might happen, okay? And what I showed you was, by the way, the general solution to this problem, or let's say the only solution to this problem that is known, is to use continued functions. So what's the point of a continued function? You see, you have found a representation of the answer as a Taylor series. Now, this isn't really a Taylor series, we're going to learn. That's because it doesn't converge. If it doesn't converge, it's not a Taylor series. It looks like a Taylor series, but it isn't a Taylor series. Okay? And so this is actually not, this symbol here is actually not the symbol to use, and we're going to see that the correct symbol to use is this symbol, and this series is called an asymptotic series, okay? But before we get ahead of ourselves, this is a Taylor-like series. And it doesn't converge because you're outside the radius of convergence of the series, okay? In fact, the radius of convergence of the series is typically 0, okay? Nevertheless, there's something we can do, as I said, which is to use continued fractions, or continued functions. We're going to use today continued fractions. And the objective is to find a different representation for this function. And this representation, we hope, will be a convergent representation. Now, to introduce you to this idea, I showed you last time, I showed you the notion of a continued exponential. Okay? So you begin, let's get this. Okay. So to begin, you've got some sort of Taylor-like series to sum. Okay? And what we did was to construct a set of simple algebraic formulas. And what this formula does is it shows you how to go from the coefficients C sub n in the Taylor series to the coefficients A sub n in a continued in a continued exponential. Okay? So we converted the problem of evaluating a Taylor series to the problem of evaluating a sequence of approximants. Okay, and this is the word that you use in the business. Okay. We have to construct a sequence of approximants to the answer. Okay, and what are the approximants? This sequence looks like this. The first term in the sequence, if we're talking about a continued exponential, is a, and the next term is a0, e to the a1z. And the next one is a0, e to the a1z, e to the a2z. Okay? And the next one is a0, e to the a1z, e to the a2z, e to the a3z, and so on. Okay? And the question is, where does this sequence converge, for which z, and does it converge at all? If it converges, where does it converge? Okay, where in the complex z-plane? And what we're going to find is that even though the Taylor series, the Taylor-like series, does not converge, this sequence does converge to the right answer. Okay? And so if you are really, really strong, okay, and you spend another whole term working hard on your problem, your thesis problem, let's say, and you get one more term in this series, that means you are able to construct one more approximant. And that takes you much closer to the answer. Okay? Typically, approximants like these converge much faster if the Taylor-like series is divergent. Okay? Which is really wonderful. Okay? Yeah.
Just notational point. The Taylor-like series should be Cn.
Yeah, sorry. So let's call this C sub n. Okay? These are not the A's. Sorry. Yeah. Okay? And this is Cn. Okay, so do you understand the problem that we're talking about? Okay, now what I showed you was a particular example. Okay, and this is I love this example just because it's so weird. Okay, this is really weird stuff. For this particular continued exponential here, this is the Taylor-like series. So the Taylor coefficients are really interesting. They're n plus 1 to the n minus 1 power divided by n factorial. It's really strange, okay? But in this rare case, we actually have a formula for the answer, okay? And when you convert this series has a radius of convergence of 1 over e. When you convert this to this form, this sequence, the sequence of approximates that you get from this function, converge in a much larger region. And what we learned was that the Taylor series converges in this little circle here. That's a circle of radius 1 over e. But in this gigantic cardioid here, that is where the sequence of continued exponential approximants converges. Okay, it's very, very beautiful. And I showed you this picture, which I think is glorious, but we're not going to talk about it now. Okay, so what we're going to talk about today is continued fractions. And the reason is that very few people have ever heard of continued exponentials. And this is, you can't imagine how unstudied this problem is. There are very few people who've worked on it, and there are essentially no rigorous results in this field. And this is a wide open field. I mean, if you want to do a project, study a continued logarithm, or a continued square root, or a continued Bessel function, or a continued, who knows? I mean, you can do anything you like. Okay, there are an infinite number of functions. Which is the best function? Okay, and the only one that has really been studied in detail is continued fractions. Okay, and so what we are going to do, and this is really the only function, a continued fraction. This is the only thing that has been studied in detail. Books have been written about this, and there are actually some rigorous results. For all of this other stuff, there's no rigorous results at all. There's nothing. It's just virgin territory. So what are we going to do when we make a continued fraction? What we're going to do is we're going to say, suppose we have a Taylor series, let's say a sub n x to the n, okay, a Taylor-like series, and we want to convert it to a continued fraction. Okay, now what's a continued fraction? A continued fraction is something of the form, let's call these coefficients b sub n, okay? And a continued fraction is something of the form a0 over 1 minus a, let's see, should we do that? No, actually, let's call this a sub n. Let's call this a sub n, and let's call this b sub n. So this is b0 over 1 minus b1x over 1 minus b2x over 1 minus b3x, and so on. Okay? So the idea is that you have this series, and this series diverges, typically. Okay? If you convert it to a continued fraction, the sequence of approximants you get from the continued fraction might well converge. Okay, so by the sequence, just to make it absolutely clear, what I mean by the sequence of approximants, what you would calculate on your hand calculator would be b0, b0 over 1 minus b1x, b0 over 1 minus b1x over 1 minus b2x, and so on. That's what you would do. And this sequence, I claim that in many cases, this sequence will converge to a limit, which is the correct limit, which is what this is the answer you're looking for, even though this does not converge. So this is a non-convergent representation of the answer, but it contains the information about the answer. And by doing this conversion, we can extract the information in the divergent series. That's the objective. Okay? Now, there are lots of ways of explaining this to you. Let's move this up. And I have one way that I like to explain it, which you will never see in a book, which I think is, but I think it's amusing. Okay, so I'm going to give you an IQ test. That's how I'm going to explain it to you. So I'm sure some of you, at least, have taken IQ tests for fun, and one of the types of questions they ask you is, what is the next number in the series? right? What's the next number in the series? So, so here's an IQ test for you. Does anybody know what is the next number in this sequence? Nobody knows. Not a single person is raising their hand. Okay, so I'll help you out on this one. These are the express stops on the 7th Avenue local in Manhattan, okay, going uptown. Okay. So the next stop is 125th Street, and so, okay. All right, well, okay. You don't get, okay, your IQ score is not as high as it could have been. Okay, so here's a more serious question. What's the next number in that sequence? Now, the question is, you couldn't possibly answer it. Okay, this is hopelessly complicated. But this is serious, and these are very important numbers in mathematical analysis. So you either know the answer or you don't know the answer, but you can't figure out the answer because this is ridiculous. Okay. But does anybody happen to know what these numbers are? Does anybody know? Okay, so these are the Euler numbers. Those are the Euler numbers. 1, 5, 61. And the next number happens to be 1385. Okay, and if someone walks up to you on the street and says, what are the Euler numbers? You either know them or you don't. Or if someone says, what's the next number, 1561? Hopeless, okay. But I'm going to give you an interesting way of solving a problem like this. Does anybody know the next number in this sequence? These are letters. O, T, T, F, F, S, S. Anybody know the next letter? No? I would think is obvious, right? No? It's E. 1, 2, 3, 4, 5, 6, 7, 8. Okay. All right. You have to know how to spell, of course, to do that. But all right. So imagine that you're working on an IQ test problem, and you are trying to guess the next number in a sequence. Okay? We don't know these numbers, so we're just going to call them A sub n. Okay? And this is the first number, and the second number, and the third number, and the fourth number, and so on. And we can, in fact, take A0 to be just 1, by definition. We can always take the first number to be 1. So we could really think of this as 1, 1, 2, 5, 61, like that. Okay? Now, to solve this problem, what I'm going to do is invent a transform. It's a little bit like the Fourier transform. Okay? When you solve a problem using the Fourier transform, you begin with a problem, you transform it to another problem, you solve that problem, and then you transform back again. And that's exactly what we're going to do here. So I'm going to start with the numbers A sub n, and I'm going to transform to a set of numbers B sub n. And B0 is going to be 1 by definition, just by definition. And then we're going to find a number B1 and a B2 and B3 and so on. And we're going to hope that the numbers B are much easier to guess. Okay? And then when we transform back again, we will know the answer. So the idea is you couldn't possibly guess the next number in this sequence of A's. You can guess the next number in the sequence of b's. That will be easy. We will then find, this is the number we're looking for, we will then guess b4, and then we'll transform back again. We'll get the answer. Got it? That's the plan. So I propose that we do this in 3 very, very easy steps. Okay? So here it is. Step 1. Okay. So I'll write it down. Given the sequence A sub n, I want you to imagine that A sub n is the 2nth moment of some function. Okay? So I want you to imagine that A sub n is the moment, let's say it's an integral from minus L to L, of some function, some weight function, w of x times x to the 2n. Okay, now this is called a moment. This is called a moment. These are moments, okay? Now, of course, we don't know what L is. And we don't know what the function w is. In fact, there's a very, very, very famous problem called the moment problem. Okay, and the moment problem consists of my telling you A sub n for all n. And you have to find the function w. You have to go from the numbers A sub n to determine the function w. That's an extraordinarily hard problem. If you can make progress on this problem, publish it. That's your thesis right there. Okay, this is a very, very hard problem. So make sure you understand what I'm saying to you. I am not telling you to solve the moment problem. I'm not asking you to find L or W. I'm just asking you to imagine that these first few numbers are these moments, that they can be written in that form. Okay, did you get done imagining it? It should take you almost no time, because now you've imagined it. Okay, I didn't ask you to do anything, I just asked you to imagine it. Got it? Okay, good. That's step 1. Okay? Now, step 2. Suppose you had a bunch of numbers. Suppose you have a bunch of numbers called b sub n. Okay? What could you do with the numbers b sub n? Well, I claim that it would be fun to use those numbers to construct a bunch of polynomials. Okay? Now, I'm not asking you to construct the polynomials. I'm just asking you to imagine that you can construct the polynomials. According to the following rule, you could say the 0th polynomial is just defined to be 1, and the first polynomial is defined to be x. It's a simple polynomial. And the n plus first polynomial will be defined as x times Pn minus Bn times Pn minus 1. Okay? So imagine that you knew the b's. Of course, you don't know the b's. But if you knew the b's, you could use this formula to generate a sequence of polynomials. Couldn't you? In fact, let's do it. Let's just for fun, let's do it a little bit. I mean, I'm not going to waste your time. But we could construct these polynomials. So, for example, if you wanted the second polynomial, you'd go to this formula here, you'd plug in n equals 1, and you would see that the formula is x times p1, which is x squared, minus b1 times p0, so it's minus b1. So there's the second polynomial. If we wanted the third polynomial, P3, the formula says take x times the second polynomial, which would give you x cubed minus b1x. Okay, and then minus b2 times the first polynomial. Okay, so it would be minus b2 times x, and there's the polynomial. It's not very deep. And just for fun, let's find one more polynomial. How about P4? P4 would be x times this times P3, which would be x to the 4 minus b1 plus b2 x squared. So it's x times this, okay? And then minus b3 times p2. So it would be b3 times this right here. So it would be plus b3, okay? And then b3 times b1 would be plus b3 b1. Okay? Do you agree? Is that okay? All right. So we could just go on like this and have fun and making polynomials. By the way, these polynomials are called monic. Okay, these polynomials are called monic. Do you know what monic means? That's a big word, but it means something rather trivial. Anybody know what that means? Say, that's right. The coefficient of the highest power is always 1. By construction, you can see that will be true. So the coefficient of x squared is 1. X cubed is 1. X to the 4 is 1. And that's just because this rule says you always multiply the previous polynomial times x. So the highest power is going to be, coefficient of the highest power is going to be 1. That's not terribly important, but it's true. Okay, so let's see. Let's push this up higher. And we'll push this up a little bit higher. Okay, so that's step 2. So I said we were going to do this in 3 easy steps. Do you agree that the first 2 steps are pretty easy? Hope you do. Okay, so good. We're up to step 3. So far, if you had, let's make sure that you're following this. If you had the numbers a, all you were supposed to do with them was to imagine that they could be the 2nth moment of some function. And if you had the numbers b, all you have to do is imagine that you construct these polynomials. But so far, there's no connection between the numbers a and the numbers b. We need a connection. Can anybody guess what is the connection we're going to establish between the a stuff and the b stuff? What would you choose as a connection?
Integration.
Integration. Integration? What do you mean by that?
You bring in the W and integrate and see how it relates to.
Yeah, and what would be the condition that you're almost there? But what is the condition that you're looking for? You're almost there.
I guess you want to equate the lower powers first, or the lower.
Well, we're not equating powers, but we're looking for a fundamental thing about the polynomials. Anybody have an idea? The most interesting property of a set of polynomials would be that they're orthogonal. So let's require that these polynomials are orthogonal with respect to what?
W.
Say again?
W.
W. That's right. Let's require that if we integrate from minus L to L, Pn of x times Pm of x, where n is not equal to m, that we get 0 if we integrate with respect to the weight function w. That is going to be the connection. Okay? I mean, what else? There isn't really anything else. If you have a set of polynomials, the most interesting property they could have is that they're orthogonal polynomials. Okay? So the dot product of these vectors is 0. Okay? Now, we're not saying the polynomials are orthonormal. Okay? That would be some statement about what happens when n is equal to m. But we're assuming that if n is unequal to m, that these polynomials are orthogonal. So, for example, if that's true, let's assume, by the way, that this function w is an even function. That's why I'm calculating even moments. Otherwise, for odd powers, if this power of x were odd, we would get 0 just by oddness. Okay? So let's require, for example, that p0 is orthogonal to p2. That's a non-trivial condition. Okay? So if we multiply p0, which is just 1, times p2, and integrate, now let's assume that the 0th moment, we're assuming, remember we assumed up here, we assume that the 0th moment, the integral of the function w itself is just 1. Remember a0, which is the integral of w from minus L to L, that's just 1. We made that assumption. If this assumption isn't true, we just multiply all the numbers by a constant so that it's true. Doesn't matter. Okay. So if we require this, then that says that the integral of p2 must be 0. And that says that a1 minus b1 is equal to 0. Do you all see that? Just integrate p2. Does everybody see that? Are you all with me? Okay, any questions? So this is good, that's fine. That tells me that a1 is equal to b1. Good. Okay. Okay, good. So what's another requirement that we can place on our polynomials? What if we require that p0 is perpendicular to or what if we require that p1 is perpendicular to p3? That's a simple requirement. Okay. So we take p3, we multiply by p1, which is just x, and we integrate. So the first term would be x to the 4, and the integral of x to the 4 is a2. And the integral of the second term, that's just x squared, gives me a1. So it says minus b1 plus b2 times a1 is equal to 0. Okay? But we already know what a1 is, right? We already know a1. a1 is b1 from this equation here. So that says that a2 is equal to b1 times b1 plus b2. A2 is b1 times b1 plus b2. Okay? What's another interesting condition? What if we require that P4 is orthogonal, P4 is orthogonal to P0? Got it? Said? Okay. So let's see what that says. If you multiply P4 here, this is P4, times P0, which is just 1, and we integrate, here we get the condition A2. Over here, you get the condition minus B1 plus B2 plus B3 times A1, right, which is B1, okay, plus B3, B1 equals 0. Okay? Now, let's see. Here is a plus B3, B1. Here's a minus B3, B1. So those guys cancel. And we learn that A2 is equal to B1 times b1 plus b2. Woo! We learned that already. This is not new. That's not new. We knew that already. Great. Okay? That's amazingly lucky. What if we got a different formula? Then the whole thing would collapse. You understand that when you require that all these different polynomials be orthogonal, you might overdetermine. But in fact, you precisely determine the condition. You have just enough information and not too much information. So there's no contradiction. This is not new, but it is the same formula that we already had. Whew. Okay. That's good. Okay. So can we make a new condition? Well, let's require that P4 is perpendicular to P2. So let's take this P4 over here and multiply it by P2 over here and integrate. Now that looks like a mess, but it isn't a mess. Why not? Because we've already multiplied by a constant and integrated, and we got 0. That's what we just did. So now I'm going to multiply by x squared and integrate. You got it? You with me? So if I multiply by x squared, multiply this guy here by x squared and I integrate, the first term gives me a3. The next term gives me minus b1 plus b2 plus b3 times a2. And the last term gives me b3 b1 times multiply by x squared, and I'm integrating, right? So I get a1, which is b1, so b1 squared. That is 0. That's what I conclude here. Okay? So this seems to be a formula for a3. So this says a3 is equal to b1 plus b2 plus b3 times a2. But we just got a formula for a2. We learned that a2 is b1 times b1 plus b2. b1 times b1 plus b2 minus b3 b1 squared. That's the formula for a3. And we could simplify this a little bit. We could take the first two terms here and multiply that out. That's b1 times b1 plus b2 squared, right? And the last term is b3 times b1 times b1 plus b2 minus b3 times b1 squared. That's this term. And you notice that there's a b3 b1 squared right here minus b3 b1 squared. Okay, so that guy cancels. Yeah? Sorry? P2 times P4. Yes, as I explained to you, we have already multiplied by a constant and integrated, and we automatically got 0. That's what I learned when I did this calculation. Got it? So it simplified the calculation. So I only needed to multiply by x squared. Got it? Okay, so therefore, I learned that a3 is b1 times b1 plus b2 squared plus b1, b2, b3. Okay? And you agree that we can continue this, but I could program Mathematica to do this. I don't have, grown-ups shouldn't waste their time crapping around like this. But I get a bunch of formulas, okay? And do you agree that if I know the b's, if I know the first 23 b's, I will know the first 23 a's. But if I know the first 23 a's, I will know the first 23 b's. You see that? Okay, well, in our case, you remember our case? This sequence here. Let's see what happens. Okay? So, first of all, A1 is 1. So if A1 equals 1, that tells me that B1 is 1. That comes from this equation. And if A2 is 5, that tells me that B2 is what? 4. Okay, good. And if A3 is 61, that tells me that B3 is A3 is 61. Okay, this guy here is 61. B1 plus B2 squared would be what? 25. 25. And B1 here is 1. B2 is 4. So if you take 25 away from 61, you get 36. And you divide by 4, which leaves 9. Okay, So B3 is 9. So 9. Okay, now. Okay, remember, you remember the scenario. You're sitting in an office, and this really dull and boring IQ person who couldn't possibly solve the problem themselves says, I'm testing your IQ. What's the next number in the sequence? And they say 1, 5, 61. Okay. What do you say in your head? In your head, you say 1, 4, 9, 16. Okay. Now you go back again, and if you do go home and do it, it'll take you 2 minutes. You'll learn that A4 is 1385. So you say 1385. The person who's testing you says, all right, test is over, go away, you've gone off scale. Okay, can't measure your IQ anymore. Okay, all right, so that's the end of this discussion. The question is, what does this have to do with? This is really crazy. I mean, it's interesting, but what does this have to do with? Well, it has to do with continued fractions. In fact, let's lower this. You remember I said you are given a divergent series, okay? And the coefficients in the series are this. This is the sum from 0 to infinity. A0 in this case, just for simplicity, we take that to be 1. And I said, can you convert it into a continued fraction of this form? Well, the relation between these A's and these B's are precisely these relations. That's the connection. Okay, of course, maybe you're not so fancy. You don't have to be fancy schmancy, right? I mean, if you really wanted to calculate the B's, all you have to do is expand this in a Taylor series and compare the terms, okay? So, of course, we've taken B0 to B1, but if you just write down the first 2 terms in this series and the first 2 terms in this series, what do you get? Well, the first 2 terms on the left are precisely A0, which is 1, plus A1x, and so on. And if you take this and just take the first 2 terms in the continued fraction, that would be 1 over 1 minus B1x, right? And now if you expand this in a Taylor series, okay, you expand this in a Taylor series, what do you get? 1 plus B1x. And now when you set this equal to this, you learn that A1 equals B1. And that's precisely the first of our formulas. That's this formula here. Okay? And if you take the first 2 terms in this series, and you take the first 2 terms in this series, and you expand it in a Taylor series, you'll get the next formula. Okay? So there's a very deep connection between continued fractions and orthogonal polynomials. It's very interesting. But there's something even more interesting, and that's really quite fascinating. if, and the statement is this, if the numbers a sub n, if a sub n are growing very rapidly, as they do in perturbation theory, if a sub n grow like, say, n factorial, then the b sub n grow like n. Just like n. They're just linear in n. It's very interesting. And if a sub n grows like 2n factorial, very, very rapidly, then the b sub n grow like n squared. So the b sub n are very moderate numbers. They're not growing very rapidly. Very well-behaved, very moderate numbers. And indeed, the Euler numbers, E sub n, those are the Euler numbers, 1, 5, 1, 5, 61, 1385. These numbers are growing roughly like 2n factorial times some constant to the n for large n as n goes to infinity. Okay? And that's the reason that in our case we found that the b sub n's grow like, the b sub n's here grow like n squared. So the b sub n's are very well behaved. Okay. Now, okay, are there any questions at this point? Are you following what I'm saying? Because what I'm about to show you is just sheer beauty. I mean, it's just magic. It's just unbelievable magic, okay? But so far, everything I've told you is just, a bunch of observations about mathematics, okay? So the question is, so if you have, you agree now that if you have a Taylor series, a sub n x to the n, a formal Taylor series, which may or may not converge, and typically it doesn't converge, what you can do is convert this into a sequence of continued fractions of the form b0 over 1 minus b1x, b0 over 1 minus b2x, 1 minus b1x over 1 minus b2x, and so on. Okay, so we've converted a Taylor series, which you cannot sum up, into a sequence of numbers called approximants, and these are continued fractions. There's just one more very simple step. If you wanted to, this is junior high school this is trivial mathematics, but if you wanted, you could rewrite this in a relatively simple form. Do you notice that this is just a number? This b0 is just a number. It's 1. And we could think of this number as being 1 divided by 1, just for fun. Okay? And we could think of this structure here as a number, just a pure number. And if you don't mind, let me write this number as, say, let's take, this is not the same polynomial we had over there, but this is a polynomial of degree 0, that is just a number. So think of this as a polynomial of degree 0 divided by a polynomial of degree 0. Okay, and this is a polynomial of degree 0 again, just a number, divided by a polynomial of degree 1. Okay, it's 1 minus b1x, but it's a polynomial of degree 1. And now I want you to look at this. If you were to rationalize this, you know what I mean by just multiply the top and the bottom by 1 minus b2x, okay? You could write, well, let's do it, because this is easy. Multiply the top and the bottom by 1 minus b2x. So you get b0 times 1 minus b2x, and then in the denominator you'd have 1 minus b2x minus b1x, right? So this is a polynomial of degree 1 divided by a polynomial of degree 1. Okay? And the next term, if you rationalized it, would be a polynomial of degree 1 divided by a polynomial of degree 2. And the next one would be a polynomial of degree 2 divided by a polynomial of degree 2. And next one would be a polynomial of degree 2 divided by a polynomial of degree 3. And then P3 over P3 and so on. This is not the same polynomial. This, I just mean, do you understand the notation I'm using? Just a third degree polynomial, some third degree and some other third degree polynomial. You all understand what I'm saying? When it's written in this form, this is called a Padé sequence. Okay? So it has a name, Padé sequence. And what? Manual. Ah, thank you. Okay, just go a little bit higher. Okay. And in general, what I could do here would be, I can actually do something a little bit more general than this. I could do the following. I could say, let me take, from this sequence, let me take the first n plus 1 terms in this sequence. Okay, so let's take the sum from 0 to n, a n x to the n. So this is, altogether, in fact, rather than, let's not take n terms. Let's take, let's take p terms plus q terms. Okay, so altogether, there are p plus q plus 1 terms here. So there are p plus q plus 1 numbers a sub n. And I could convert this, if I wanted, I could convert it to a fraction where I have a polynomial of degree p and another polynomial of degree q. Now let's make sure that we understand what we're saying here. I have a polynomial of degree p divided by a polynomial of degree q. How many coefficients are there in a polynomial of degree p? Say again? P plus 1. Okay? And in q, q plus 1. So there would be p plus q plus 2 coefficients. But this is a ratio, right? Therefore, without loss of generality, I can assume that the coefficient, let's say one of the coefficients, doesn't matter which one of the coefficients is automatically 1. Okay? So we really have, here we have p plus 1 pieces of information, and here we have just q pieces of information, because one of them, without loss of generality, can be taken to be 1. So there are p plus q plus 1 coefficients that we need to know, and there are p plus q plus 1 pieces of information we have. So if we expand this in a Taylor series, then, and we set the terms here equal to the terms there, I can find formulas from all of this information for all of these coefficients. Do you agree? Is that clear? You can do that. This is just routine. So what I have done, what do we call this? We call this the generalized Padé approximant. So this, we'll call this Padé, P for Padé, and I'm going to write a superscript P and a subscript Q. Okay, so I can convert the first, any number of terms in a Taylor series, into this Padé. Okay? So I have a matrix of Padés. I have a table of Padés. Okay? This is, p equals 1, p equals 2, p equals 3, and so on, and have q equals 1, q equals 2, q equals 3, and so on. And I can fill in all of these Pades. Okay? This particular sequence of Pades is called the main Pade sequence, or the diagonal Pade sequence. So these are the Pades that go right down the diagonal in a stepwise fashion, like that. Does everybody understand? And these are the ones that we mostly work with, although this is the more general case. Okay, that is the technology that I wanted to teach you today, and I want to give you some examples now, because this is just sheer magic, what you're going to see. Okay, but are there any questions about how you do this? Do you understand the notion of Pade? So, again, you have a Taylor series, a formal Taylor series that does not converge. So what do? It's hopeless. We can't add it up. It's not an acceptable representation. So instead, we convert it to a bunch of Pades. The question is this progress? And the amazing thing is, it's absolutely amazing, typically, this Pade sequence converges. And it converges very rapidly. Really, really rapidly. Okay? Yeah.
It seems like magic.
It's magic. Right. And I'm going to tell you, so some theory, some rigorous theory is known. Okay? And this theory, much of it is due to the work of Borel and a few other mathematicians, mostly French mathematicians, okay? And it is the, how do I say it? It's the antidote to what they teach you in classes on quantum field theory and on quantum mechanics. Because in a class on quantum mechanics, they teach you, or quantum field theory, they teach you perturbation theory. And without teaching you this, it's junk. Because you can't do anything with what you've learned. You calculate a bunch of Feynman diagrams, big deal. But you convert that to Pade, and now you can sum it up. Okay? So, just as an example, let's push this up. Okay, just as an example, when you work on the anharmonic oscillator, whose Hamiltonian is p squared plus q squared over 4, or x squared over 4, plus epsilon x to the 4th over 4, and you calculate the ground state energy, which is a problem that you've been assigned, right? You've assigned that problem. Okay, so you find that the ground state energy as a function of epsilon is 1/2 plus 3/4 epsilon minus 21/8 epsilon squared. Okay. This is a wildly divergent series, and this series diverges. The nth term in this series, a sub n, is roughly n factorial. That's how rapidly it's growing. More precisely, it grows like n factorial times 3 to the n, roughly, as n goes to infinity. Wildly divergent. A zero radius of convergence. When you convert it to Pades, the Pade sequence converges rapidly. Okay? It converges very rapidly, and it converges to the right answer. In fact, it's even better than that, because if you work out the Pade sequence, this is the way it converges. So if you plot the PNNs of epsilon, PNN, okay, that's half of the numbers in the Pade sequence, the PNN. This is the exact answer. And this is n. Typically, what you discover is that these converge in a monotone decreasing fashion. and approach the exact answer from above. And the Pn plus 1s converge like this. And they approach the exact answer from below. Okay, now I want to see how much you've learned. So you understand, we have a sequence here, and it's approaching the exact answer. Okay, that is, the exact answer means E0 of epsilon, the energy that we're looking for. This is a physical answer to a physical problem. Okay, and you have a sequence, and this sequence gives you a bound on its own error. You know how big the error is, because if you take two subsequent p's, you know the exact answer is trapped in between those two numbers. But what's more, the sequence is converging like this. Okay, what do? Shanks, that's right. In fact, you can extract even more information from the PADEs by doing a Shanks transform of the PADEs. And if you do that, instead of convergence like, here's the exact answer, instead of convergence like this, instead of that, if you Shanks this, you get okay, so you can extract fantastic amount of information. Okay? Are you beginning to feel how much power you have? Okay, so let me talk a little bit about PADE, and what I want to do is give you some examples. Okay, now, first question is, can you read these numbers? I'm sorry for there being a lot of numbers here, but that's the only way. I mean, this is an advertisement. Okay, so as an advertisement, I have to show you, where did I put it? Here, let's use this. Let me sort of explain what is going on here, okay? So, first of all, consider the Taylor series for the function e to the x. The Taylor series for the function e to the x. Now, if you had the Taylor series for the function e to the x, here's where should we, let's put this here. Okay, if you had the Taylor series for the function e to the x, now here I'm evaluating it at x equals 1. We're going to evaluate it at x equals 1. But we have the Taylor series for the function e to the x. You know that this Taylor series has the form sum from n equals 0 to infinity, x to the n over n factorial. Is that a convergent series or not? For which x does this series not converge? There's only infinity. For all finite x, this is a rapidly convergent series. Before you took this course, if somebody said, what is e of 1, for example, what happens if we set x equals 1, you would have said, are you kidding? I can calculate e of 1 really well, because you know, all I need to do is to sum the series 1 plus 1 plus 1/2 plus 1/6 plus 1 over 24 plus 1 over 120 and so on. And this is a rapidly convergent series, and who needs, I mean, this is kid stuff. Okay? But let's see what happens. Let's see what happens. This is what happens if we're adding up the Taylor series. This is what happens if we add up the PADEs. That is, we calculate the diagonal PADE sequence. Okay, so here's P00, P01, P11, P12, P22, and so on. Okay? And the question is, if you look at the PADEs, these guys look the same. Right? If you look at these numbers, they're the same. Okay? But you can ask, how much error, what's the percentage error between the exact answer, E is the exact answer, and these numbers and these numbers. So looking at these numbers is not really very useful. This is the error, okay? Notice that if you use the 4-4 PADE, that is 8 terms, the Taylor series out to x to the 8, to calculate the 4, pod A, the Taylor series is accurate to 1 part in 10 to the 6. But the pod A is accurate to 4 parts in 10 to the 8. Pod A is better. So you don't add up the Taylor series. You first convert it to a pod A. Okay? If we calculate the 10-10 pod A, the error is 1 part in 10 to the 25, whereas the Taylor series is only accurate to 7 parts in 10 to the 21. So the pod A is about 100,000 times better than the Taylor series. It knows the answer. It's magic. Okay. Now, in this particular case, you can prove it. There's a rigorous proof that the pod A converges and that it converges faster. Okay? Well, you say, oh, right, come on. I mean, I'm a cosmologist. 2 decimal places make me happy. Who needs 25 decimal places? All right. Okay. So let's do a different one. Let's do the same problem, except let's try to sum the Taylor series at x equals 5. Okay, now the Taylor series doesn't converge so well because this is not the right series to add up, but rather here there's a 5, and here there's a 5 squared, and here there's a 5 cubed, and here there's a 5 to the 4, and here there's a 5 to the 5. So the Taylor series is kind of slow. It's not converging so rapidly. It is going to converge, of course. We believe, right? You have a belief system. You believe that Taylor series. Okay. However, let's look at the error. You notice that if I calculate the 1313 pod A, the error is 8 parts in 10 to the 17. But the Taylor series is only accurate to 5 parts in 10 to the 12. Okay? Much more efficient. Okay? Over here, 10 to the 8, 10 to the 11. The pod A is uniformly better than the Taylor series. Okay, so now I can ask you a very deep question. Is that the best you could do? I don't believe that for a second. Okay? And if you do some serious research, I mean really serious research, using principles of information theory and so on, you will you'll find that I'm sure that there may well be an optimal machine for extracting information from a Taylor series that converges. But remember, in this problem, we began with a series that already converged, and we used pod A on it. Okay, so we had a series that already converged. Here's another series, and this is an example of magic, because nobody knows why it works. Okay, but if you take the Taylor series of the gamma function. Now, actually, this is not the gamma function, because what do you know about the gamma function? The gamma function has poles. Okay, so I hope you know this. If you make a plot of gamma of x as a function of x, gamma of x blows up at 0, and then it grows very rapidly, like x to the x, e to the minus x here. But then there are poles at all of the negative integers. Every negative integer, the gamma function blows up. So this is 0, minus 1, minus 2, minus 3. So it blows up at 0. It comes up from minus infinity. It blows up again, comes down from plus infinity, blows up again, up from here, up from here, up from here, up from here, and so on. So they're poles. So a Taylor series in powers of x has a 0 radius of convergence because there's a pole right at 0. However, do you know that 1 over gamma of x is entire? It has no singularities at all. Okay? Therefore, you can write down a Taylor series of the form a sub n x to the n, sum from 0 to infinity, and the radius of convergence of this Taylor series, like the function e to the x, is infinity. This is great. There's only one thing wrong with this Taylor series. You can't use it for anything. By the way, to begin with, calculating the coefficients in this Taylor series is a monster, because these coefficients require a terrific amount of numerical analysis to calculate, because they're given in terms of zeta functions. Okay? But if you look at the Taylor series and you look at the Pades, okay, here are the NN Pades. Here are the n plus 1 Pades. The Taylor series doesn't work at all. Okay? So here are x equals 1, x equals 2, x equals 4. I took 4 different values of x. If you try to use the Taylor series, you cannot get an answer. But if you use the Pade, you just can't do it. If you sum up, for example, that Taylor series at, say, x equals 4, it will say that gamma of 4 is 1,000,000 or something like that. You have to go many, many, many dozens of terms before it even vaguely resembles the correct answer. Taylor series is an obnoxious series. Even though it has an infinite radius of convergence, it's obnoxious. But if you calculate the Pades, they converge to the right answer. Okay? At x equals 4, the right answer is 3 factorial, which is 6. And this is what I learned from the Pades. If you use the Taylor series, you have to take maybe hundreds of terms before you know that gamma of 4 is 6, which is 3 factorial. Okay? And this is what I get from the Pades. Look at the Pades converging to the exact answer. 1. At x equals 2, gamma of 2 is 1. Gamma of 3, 6, and so on. Gamma of 4 is 6. So the Pades extract the answer from a Taylor series that is essentially useless. Okay? Nobody knows why. It just works. It's just fantastic. There's no proof. It's just an experiment. Hang on just a bit, and I'll show you. Just want to show you a few more things. These two series were convergent series. Now I want to give you a series that is not a convergent series. So I want to look at the function log of 1 plus x over x. You see that? 1 plus x over x. So let's just a second, let's just look at that. Log of 1 plus x over x. What is the radius if I expand this into a series of the form a sub n x to the n? Can anybody tell me the radius of convergence of this series? In powers of x. Say it again? 1. You're right. Thank you. Very good. Why is that? Why is the radius of convergence 1? That's right. There's a singularity at x equals minus 1. Okay, you notice there's a 1 over x here, but this is not singular at 0. Do you all understand that? Why is it not singular? Because the log of 1 is also 0. So at the origin, this function is not singular. But there is a branch cut at x equals minus 1. So in the complex x plane, there's a singularity at minus 1, which is a branch point singularity, and there's a branch cut running like this. But the Taylor series converges in a circle. So what I did was to calculate the Pades at x equals 1/2. The Taylor series converges at 1/2. And then at x equals 1, the Taylor series does not converge at 1. And then at x equals 2, the Taylor series definitely doesn't converge at 2. Okay? And if you calculate the Pades, here is the nn Pade, and here's the nn plus 1 Pade. You notice, remember what I told you about the Pades? You notice that these numbers are gradually getting smaller, coming down from above. And these numbers are gradually getting larger, coming up from below. And do you notice that at 1/2, look how accurate the Pade is? Okay? The answer lies between 810-930-2162 and 810-930-2162. Okay? And that's the 8-8 or 8-9 Pade here, and this is the 8-8 Pade. Do you see that? Now, let's go to the place where the Taylor series doesn't converge, right at x equals 1. The PADEs are coming down from above, they're coming up from below, and look at the convergence. Okay, look at this. 693,147, 1806, 693,147, 1806. And the answer lies between those two numbers. Okay? All right, now let's go deep into the region where the Taylor series no longer converges. Look at the convergence of these guys at x equals 2, and look at the convergence of those guys. And the answer lies between 549, 306, 1445 and 549, 306, 1443. Okay, and these are converging downward, and these are converging upward, and the correct answer is trapped in between. So we even know what the error is. This is an example of a function of Stieltjes who is the most, who's done the most amount of work on this class of functions. And it is rigorously known that this convergence really happens. So in this case, you can prove that the PADEs are converging in a monotone fashion like this to the correct answer. Okay? Okay, now there were some questions, and I think this is as far as I should show you today. Next time, I'm going to show you what happens when we study Taylor series that have a zero radius convergence, like the series that you get when you solve physical problems. Okay, did you understand what we did? This is unbelievably, it has an element of mystical about it, but you see how many problems there are left to be done. This is frontier mathematics, and this is really, really powerful. This is the reason why we can teach you physics. Okay, because when you get your answer, you can sum it up. And in the case of quantum mechanics, you can prove rigorously that you have a function of Stieltjes, and therefore, for this divergent series, the answer converges in that monotone fashion, from above and from below. Okay, are there questions about it? Yes. Oh, you had a question. That's right.
Previous slide with gamma function series, and why is there no monotony there?
I'm sorry, why is...
it's not monotonic there.
It's not monotone. That's right. In that case, it's not monotone because it is not a function of Stieltjes. Okay? So if you know that the function you're calculating, like, for example, the energy level of a quantum mechanics problem, here's the energy level. In this case, it is a function of Stieltjes. But in the case of the gamma, and therefore rigorous theorems can be proved, have been proved. But if you have some other function, like the Taylor series for the gamma function, that is not a function of Stieltjes. And that's why people don't know anything. And yet, the PADE still works, obviously. I mean, when you look at the numerical results, the PADE is working. Why? I don't know. It's magic. Okay, now actually I can give you, let me give you an intuitive explanation. Okay, let me give you an intuitive explanation of why it's working. Should I? Yeah, it'll take a second. I'll give you just an intuitive explanation. When we construct a PADE, that PADE is a polynomial divided by a polynomial. The polynomial in the denominator has zeros, and therefore the PADE can have poles. Now, what is wrong with the gamma function is that it has poles. Okay? The gamma function has poles. Okay? If you construct a PADE of this gamma function, the PADE can build in those poles, but a Taylor series can't. Got it? The Taylor series can't, because it's just a polynomial. But when you have a ratio of polynomials, you can mock up, and that's the word that the mathematicians use. It's a technical word. You can mock up the poles, and you can mock up the zeros. So you can incorporate those poles and those zeros. And those poles are approaching the correct values, and the zeros are approaching the correct zeros, which is something that a Taylor series doesn't have the ability to do. That's right. So a Taylor series is really a stupid series, can't do much. Okay, whereas a Pade can incorporate zeros and poles because it's a ratio of polynomials. So it's much more flexible. It's a much more flexible way of representing a number. It's better than that, however. You see, a Taylor series, if it converges, must converge in a circle. But a Pade is smarter. A Pade doesn't have to converge in a circle. It converges typically in a cut plane. Now you notice what's wrong with this function is that it has a cut over here. And since a Taylor series, if it converges, has to converge in a circle, it couldn't possibly converge in this circle because there's a cut in the circle. But the Pades, the region in which the Pades converge, typically looks like this. It converges everywhere except on a line. And that's precisely where this function is no good. So Pades don't have to converge in a circle. Typically they don't. They converge in a cut plane. And because of that, Taylor series are hopeless, because Taylor series are trying to do too much. Pades are wonderful because you don't ask them to do as much. You don't ask them to converge everywhere. You say, you have to converge, but you don't have to converge on that line. And in the case of the gamma function, why is that good? Because the gamma function is sick on the negative axis. It's blowing up here and here and here and here and here. But the Pades don't have to converge there. So you don't ask the Pades to do so much. Therefore, the Pades are very friendly and they're very nice to you. And when they converge like a shot. Taylor series is hopeless. Pades are wonderful. So Pades are a much better representation of the function that you're trying to calculate. However, what I just said to you was not rigorous in general. It's partly rigorous, but it isn't in general rigorous for arbitrary functions. And therefore, there's a lot of magic in that. So it's just an intuitive explanation. It's not a rigorous explanation. Okay? But it is rigorous for a special class of functions called Stieltjes functions, which we're going to talk about. Okay? Okay. Any further questions? Okay. Yes.
Example that we use to construct the
Just to
ratio
show
of
you, I
polynomials.
use the continued exponential as an illustration of a continued function. You've now seen two continued functions. One of them is a continued exponential, which I showed you just for fun. But this is more serious. This is a continued fraction. But there are an infinite number of other continued functions that have to be investigated. You could write 1,000,000 papers. You could take a continued hypergeometric function and a continued Bessel function and a continued square root function and a continued logarithm and endless amounts of interesting analysis that have to be done. That's not been done. And you will come up with a different definition of a sequence of approximants. Okay? And those approximants are very likely to converge better than the original Taylor series converged. Okay? But think about all the interesting work you can do. It's a wide open field of research. Okay? Yeah.
Why Pade converges on the cut plane? Why the cut?
Yes, and we're going to talk about that a little bit when we talk about Stieltjes functions. So you'll see that there's something special about converging in the whole plane and converging in the cut plane. Okay, Taylor series hate you because you force them to converge in the whole, in a full circle. That's too much for a Taylor series. It just goes go away. I'm not working for you today. Okay? Whereas pod A, you don't force it to converge over here. You're not requiring it to converge, and it doesn't converge. And therefore, where it does converge, it converges much better and much faster than a Taylor series. It's wonderful. Okay? It's really wonderful. It has to do with different representations of the same function. And pod A's are much better ways to represent functions than Taylor series. Why do we use Taylor series at all? Because we're forced to do perturbation theory. We don't know how to do perturbation theory in terms of pod A. So we first find the formal Taylor series, and then we convert to a pod A. Got it? It's a two-step process. Okay, any further questions? Yeah. I will give you